Hello, here's another question looking at moments of inertia. So we've got a wheel that can be modelled as a uniform hoop, mass 6m, radius 2a, attached to 6 equally spaced uniform rods, mass m, length 2a, as shown in the diagram. Okay, right, so we've got we've got all this going on. The wheel can rotate freely about a fixed axis perpendicular to its plane and through the centre of the wheel. Right, show that the moment of inertia of the wheel about its axis is that. Right, so I mean, you could put, usually they give you, you could look up the moments of inertia of all of these, but let's have a quick reminder of how we work these things out anyway. So when we were with the hoop, so we're wanting to sum up essentially we're doing an integral of mr squared is what we're trying to do here. The mass, the fraction of a mass that we're going to have going around here is going to be a d theta over 2 pi. And then we're going to integrate over angle going all the way around the circumference of the hoop. This is something I've done on a separate video. So the radius is constant on all of this. So we're going to do an integral from 0 to 2 pi of d theta over 2 pi. That's our mass bit, multiplied by the mass of the whole hoop. And then we've got to multiply by radius squared, which is also a constant. And I've gone for a capital M and a capital R here as a sort of general mass and radius of the hoop. And we can put in the 6m and 2a in the question later on. These are all constants except for the d theta. And that's what we're integrating over in order to get 2 pi. So that'll all end up cancelling out. And we just get left with I is mr squared. So when we put that in to the context of this question, I for the hoop part of it is going to be a 6m, and then we've got multiplied by 2a all squared. So we've got 6m times 4a squared. So we've got 24ma squared. That's for the hoop. Now we've got 6 of these individual spokes that we've got kicking around. So if we were going to get the moment of inertia for one of these spokes, and then we can just do that 6 times over and add them all up, because we can just add all of these moments of inertia together. So for this case, we're going to be integrating over the length of this over this spoke. So we're going to integrate from 0 to say length L. The mass, we're going to have the total mass multiplied by some little dl divided by the total length, so that's our mass. And then we're also going to have what the radius is at some point, which is the little l squared. So this is what we're integrating in order to get the moment of inertia of one of these rods. So we've got an L cubed over 3 when we integrate, and that is going to be from 0 to L. So we're just going to have an L cubed over 3, cancel the L's, and then we're left with L squared over 3. So we've got ml squared over 3. That's for the rod. So when we put in, what have they got? Mass of m, so that just becomes a lowercase m. So I for the rod is going to be a lowercase m. Then we've got 2a for the length, so that will be 4a squared over 3. 4ma squared over 3. So that's how you can work these things out quite quickly. But they often, quite often you'll just look these things up. So now we want the moment of inertia for the whole thing. So we're going to add this up. We're going to get our 24ma squared and 6 lots of this one. So it's 24ma squared and then 8ma squared to give us 32ma squared. So that's fairly straightforward. It's even easier if you've looked up those moments of inertia to begin with. So that's the first part done. Now we've got a light, inextensible string wrapped several times round the rim of the wheel, particle of mass 4m attached to the free end of the string. Right, okay, so we've got some mass which is hanging down here, with mass 4m. So we've got a 4 mg going downwards. We've got a tension going upwards. System is released from rest with a particle hanging freely. After time t, the wheel is turned through theta radians. Okay, assume no slipping, right? So we've got no energy being lost elsewhere, which is important in all of this. Find an expression for the angular acceleration of the wheel in terms of A and G. Okay, so we've got two bits of motion that are going on here. First of all, we've got, from the wheel's point of view, we've got a moment which is being applied to the wheel. So this moment is going to be T multiplied by the radius, because we've got the tension on the string pulling downwards multiplied by the radius. So that's a 2AT. That moment is going to be equal to the moment of inertia multiplied by the angular acceleration. So this is the angular equivalent of Newton's second law. Force is mass times acceleration. Yeah, we've got here the moment is the angular mass times the angular acceleration. So that's one of our equations that we've got. The other one is going to be on the particle itself that's hanging down, which has got a net force 4 mg minus t, is going to be equal to the mass 4m times the linear acceleration. And we can switch between linear acceleration and the angular acceleration of the disk, because they must be related. You know, if you think we've got our general finding, was it, of v equals omega r, so differentiate both sides with respect to time, we've got our acceleration is theta double dot times r. So we can put here, instead of putting F equals ma into Newton's second law, we can do theta double dot times r. So r is 2a. So let's multiply all this by 2a. So make that an 8ma and then a theta double dot. Right, so we can solve all of these. Let's rewrite the first equation to put in what I is. So 32ma squared. Well, let's divide both sides by 2a then. So we've got t is equal to 16ma theta double dot. So that's given us that. We're wanting to work out theta double dot. So let's sub that into the second equation. 4 mg minus all of that is equal to that. So 4 mg, if I just add the 16 ma theta double dot onto both sides, is 24 ma theta double dot. Divide both sides by the m, and then, yeah, we can just make theta double dot the subject. So we've got g over 6a. Is our angular acceleration, so that's radians per second squared, and that gives us the second part of the question. Now for the last part, find an expression for the tension in the string. All right, so we just need to now say what t is. Well, we're just plugging it back into this expression for t that we've got up here. So we've got 16 ma g divided by 6a. So 16 mg divided by 6, that's 8 mg divided by 3. So 8 over 3 mg newtons is our tension in the string. So again, this is all pretty straightforward stuff. I think the key thing on all of this is look how easy it is to work out these uniform moments of inertia. We did this quickly at the beginning. Look at this continued link here between linear velocity and acceleration and angular velocity and acceleration. Yeah, we can extend both of them out to have that. Yeah, we can integrate up or differentiate down. So we've got that same relationship between the two of them, and we've got this angular equivalent of Newton's second law of motion, and F equals ma for moving in circles. So all of these parts fit very nicely together, and we saw here in this bit where we flipped into using a theta double dot, an angular acceleration, rather than the linear acceleration. So it's quite easy to combine these two things. You've got one thing accelerating in an angular fashion, the wheel, and we've got another thing accelerating in a linear fashion, the particle just hanging off of it. But it's very easy to merge these together and use both types of analysis in order to combine these into a single system. So yeah, it's really nice how unified all of this is. So yeah, it's pretty easy to just extend all of your linear stuff straight over to doing angular accelerations and velocities.